Next, I want to talk about two angular momentum problems or situations that we've seen on the AP tests. The first situation would be very similar to what we did with inelastic collisions in linear momentum. Inelastic collisions, recall, are when two objects collide and stick together. In this case, I have a disk and a lump of clay. I don't know why it's always a lump of clay. Maybe just because lump of clays stick reasonably well. But let's say we have this disk clay system, and we have a disk that is not rotating with an axis of rotation in the center of the disk, and it's rotating about that axis, or has the ability to rotate about that axis, but is currently at rest. A lump of clay is thrown at it and comes in with some linear velocity. Now, right now, technically, the lump of clay has no angular momentum because it's not in any sort of rotating pattern. But we can still say that right before the collision, that it's about to go into a rotating situation, and we can convert that linear momentum into an angular momentum. And I'll show you how to do that below. What we're going to do here is say that the sum of the momentum initially is going to be the angular momentum of the disk, which is 0 because it's at rest, plus the angular momentum of the clay. And so the sum of the momentums will simply be the rotational inertia of the clay multiplied by the angular speed of the clay. Now this is where that conversion has to come in. We're going to do that the angular momentum of the clay is equal to its linear velocity divided by r, using that formula that I stressed to you can be kind of important, even though it's not on the AP formula sheet. I also have the formula for a point that is going to be rotating or going in a circular path around an axis. That's mr squared. That should be given to you on the AP test. I will note that there is one multiple choice problem in the review where they do not give you these formulas, and they should have done so. And what you need to do is say that the formula for I for a point is m times r squared. So I replace I with mr squared, I replace angular speed with v over r, and then I just simply simplify and get the sum of the angular momentum initial is equal to the mass of the clay times the distance that the clay is from the axis of rotation, that's r, multiplied by the linear speed of the clay. After the collision, the clay sticks and the disk and the clay rotate together. So now we can look at the sum of the momentum after the collision. When we did linear momentum and we had inelastic collisions, we added the two masses together and multiplied by the speed that they both had as they moved together because they were stuck. Same idea here. Instead of adding masses, though, we're going to add rotational inertias. So we'll do I of the disk plus I of the clay multiplied by the angular speed that they both have because they are rotating together. Now to finish this, if you weren't given the I for the disk, you would need to calculate it, and they would need to give you the formula that I disk equals 1/2 mr squared. And so I've replaced I disk with 1/2 mass disk times radius of disk squared, added it to the rotational inertia of the clay, which is mass of the clay multiplied by distance that the clay is from the axis of rotation squared, taken that entire quantity and multiplied by the angular speed of both of them. And maybe the problem asks you to solve for the angular speed of both of them, And now what you could do is set the sum of the momentums beforehand that I got earlier equal to the sum of the angular momentums afterwards, which I just got. And depending on what's given to you in the problem, what they're asking you to solve for, you can then start to simplify. So that's the first situation. My next video will cover the second most common